Good afternoon. I have to switch to English so our speaker can understand that. So you to suffer a little bit from my poor English. Excuse me. All right, distinguished guests, and we have all the senior professors here. People come in, and there's a Wincom Liu, and all the students, and a couple of people from industry. It's our great pleasure and honor to have Professor Wincom Liu to help us to be with us. He's going to talk about, well, from my point of view, I have a couple of days of interaction with him. That's kind of revolution of how we do engineering software based on this so-called neural network. And today he's going to do a very detailed mathematical theory. I hope only two mathematics. So in a sense that you will understand how to do that. But we also asked him to say why he want to do that in a couple of first slides. So you guys get a big picture on that. And indeed, we have that at our plenary talk 3 days ago in our ACMT meeting. Professor Liu gave a very wonderful talk on this, how this is going to proceed after we have all this engineering software this day, and now it comes with the AI. All right. Now, without further ado, I think I'm going to introduce Professor Wincom Liu, and I don't think I need to introduce that. I don't need to go too detail on it. You can check his webpage, and there's a numerous award, and you all know him from the finance community. It's been in this computational mechanics society for a long time. I've been the president of ISCM. I was the president of ISCM, and when we established ACMT in Taiwan, Professor Wincom Liu gave us a lot of support. So we can be part of affiliation nation of international society using the name of Taiwan. I think it's very rare in this very difficult situation here. Okay? So we appreciate that. And before I let Professor Wincom Liu come up, for those students, you're probably familiar with AI, but not very familiar with finite element. If you are in this case, I will tell you this probably is the transformer moment of AI. So if you know how transformer lead to this large language model, this probably is the key for engineering software to be jumping to the next stage. And if you know the transformer, there's a famous paper says, attention is all you need. And this is the case. Attention is all you need. So please pay attention to Professor Liu's talk, and let's welcome Professor Liu.
Thank you. Thank you, Professor David Chen. I hope that this lecture is not too I got my point now. I hope this lecture is not too advanced. What I'd like to talk about would be something very simple called deep learning. And I would call this thing hierarchical. Deep learning, neural network, which I call HiDeNN. That is the name of the talk. And the whole idea would be we want to marry deep learning into the classical interpolation theory. And I think that one of the theory that most of the students in engineering knows is interpolation theory. So what is the relationship between deep learning and the interpolation theory? I think that is one of the goals that I want to give here. The other concept I want to talk about is engineering software 2.0. And I'm going to give you a couple of slides explaining what it is. And the whole idea would be you want to unify learning, calibration, and solving. Okay? And solving, most of the time you do is by finite element, finite difference, whatever method you're going to use. But the other technique is called data-enabled science. Okay? So basically you use some software to generate data. Okay? And then you also do experiment. So your software might not be that fit all the experimental data, so you need to calibrate. So that's the reason I like the calibration is so important. So that you can get a calibrated software so they can generate data. So that is the reason why we want to talk about unification of learning, calibration, and solving. So the way, once you get a digital twin, which is a software, learning is just like solving. Okay, so that is the unification we talk about. Now, to give you some motivation, what we want to do, I need to go back to a couple of slides that I gave 3 days ago, or 2 days ago. Because you said 3 days, so I said, well, maybe 2 days. 2 days ago, on the applications. Okay. So this is the slide that I talk about, but mostly focus on applications. In particular, I'm talking about advanced material by 3D printing. Okay. But that is a different lecture that I will talk about. And what it is here is we try to write the software so it become an engineering AI. Okay. And the whole idea of this is
thing remarkable happening in like software development and how a lot of code was being transitioned to be written not in sort of like C++ and so on, but it's written in new ways of a neural net. Basically just saying that neural nets are taking over software.
So this is the video. And he was with Tesla. He is one of the OpenAI leaders in this case. Okay. So he introduced the word software 2.0 from a computer science point of view, in particular for the large language models. Okay. So the way he defined software 1.0 is because all the software that we have done, including finite element software, is very problem specific. Okay. And the whole idea would be if you talk about universal approximation, there's a lot of hype, but hype becomes reality. How long it takes, I do not know. Okay. But the whole idea here is now you want to solve everything. That's what ChatGPT, for example, want to do. And the key point here would be you are not going to do it problem specific. So you need to come up with a general solution technique that you can solve a universal class of problems. Now, how to do that is somebody's web's work. I want to focus on advanced material, in particular for 3D printing or manufacturing. I think that is what I like to do. Now, to do this, you need to really work with what the computer science and the hardware and software aspect. Okay. So we learn a lot from here.
This fundamentally says our challenge is to figure out how, over the next decade, we think about compute efficiency as the #1 priority.
Okay. So I showed these two slides in Thailand because these two persons, famous persons, are born in Thailand. That's my understanding. And they are building some facilities in Thailand area. And this one, actually, Jason Wong, okay, become a $3 trillion US dollars company just within this year. Okay, it briefly, #2, take over Microsoft for a short time, but right now it's around #2 and #3. And my understanding, Lisa Su is the cousin of Jason Wong. Okay, and they are not competing; they are trying to complement each other in this case. So this is, you really need to do different kinds of hardware and software, and that's the reason why the whole goal from the computer science point of view is talk about use data, design an optimized problem, and train a neural network to solve the problem. Okay. So data is mostly for all kinds of data. That's the reason why they need it. For our is a lot more and scientific and engineering data. So do we really use a generalized black box neural network? I think that's the question I want to ask, because our engineering software is a lot more focused. It will not be really that universal approximation, but I'm going to go from universal approximation, integrate the idea from interpolation theory so that I can simplify and make my neural network a lot more efficient. Then I can do calibration, solving when you solve it, you got training automatically. So I'm going to give you some examples of that one. But for this lecture, we are talking about this kinds of applications. Okay, but we want to focus on these 3 bullets here, which I gave the talk 2 days ago. But I mentioned a lot more about learning, collaboration, and solving. And I talk about an alternative to data-driven approach for product design manufacturing. And the key point would be 10 to the 21st scale. So I think if you really go back to this slide here, we are passing exascale, but this is they want to do in the hardware. But can we actually do that now? And I think I can do it, actually, in the scale computation. But it's not based on purely black box neural network. You need to do reduced order model. I think that is the fundamental mathematics. I'll give the lecture today. Okay, so I just give a brief introduction what it is. And I'm going to talk about something called mechanistic kernel, if you want to call it this. Or if you discretize kernel, it becomes an interpolation. So in mathematics, we have something called kernel learning, kernel theory. Kernel is related to fundamental convolution, which is find a kernel that operates on a function. You integrate over your domain X, but X can be n-dimensional. I think the key point is n-dimensional domain is not just space and time. We talk about space-time parameter. So that makes life very interesting. And I think that is something that kernel interpolation, they're all very similar in this case here. And I want to talk about our convolution. Convolution basically is you think about how the support of your kernel. The larger the support kernel, the more connectivity you're talking about. That's a convolution, actually. Okay, so that's a definition. Now to simplify this, like I said, we are not going to do space and time. I want to do space-time parameter. So I introduce the concept of tensor decomposition. So it's called convolution hidden tensor decomposition. And I'll give you a quick summary. What we want, the goal is to solve problems. And for the lecture notes I gave out, I actually give you some appendix on some of the mathematics behind it. Okay, I wrote this article, show you something that I believe finite element is one of the major breakthrough technology, but going through about 60 years or more before it became a technology. Okay, it started in the 40s. So I break down my paper into the birth of finite element, which is from 41 to 65. It's about 20 years interval. And the golden age, I gave a history about funding on this one in the last talk. And now all the software, okay, for example, ANSYS bought Steiner for about 770 million maybe a few years ago. And now Synopsys bought ANSYS for $35 billion. But if you look at this one, it's still pretty small compared to AI, you can talk about lots more than billions, hundreds of billions. So from this age here, I want to say what exactly is there something we can do? Finite element motion is solve any problem, space and time. Can we do beyond space and time? So this is what my proposal is: hierarchical deep learning neural network, AI. And the whole idea of this would be you marry your deep learning to interpolation theory, all kinds of interpolation theory. You need to understand that part of it. I will not go through all the mathematics because it will take a long time to understand that part, but I'll give you some flavor how we're going to do this. Okay? And then you make a decision. Can I solve beyond space, space-time problems? Because that is big data. Okay. So I'll give you a basic definition. I'm not going to read this to you. This is from the book. That's a definition of machine learning. And so the whole idea here is given the data, create the knowledge. Okay, that's the reason I call learning. Identify the pattern in the data. That's a definition of machine learning. Deep learning is a subfield of machine learning. So the computer understands the challenges of complex concepts by building the deep hierarchical, the simplified concept. So those are referenced here. So you can think about what would be machine learning is a subset of AI, and AI can have something called soft and hard AI. Hard AI is not available. Soft AI is available. And deep learning is a class of machine learning. And I'm going to look at deep learning, but I'm going to make a much smaller set of the deep learning. So that's what I'm looking for. Okay. So this is a typical way to explain what is deep learning. I'll give you a very simple here. It's nothing more than you have X, output is Y. Okay. And you can think about in mathematics, Y is some function of X. X can be a parameter, it can be space, it can be time, and parameter. The whole goal I want to do is space, time, parameter. That's X, generalized coordinates. Output is whatever you want, and in between, you want to come up with a functional relationship. In mathematics, you can put down sine, cosine, any solution of a finite element. In this case, no finite element is a interpolation theory. You come up, solve the equation, and now you have a function. Okay, the function is the interpolation theory in this case. So, the deep learning is you have many hidden layers. I only show two, and you have lots of input and say some output. The key word I want to say here is this definition. Universal approximation refers to a technique in computer science that uses a grid base, which is more or less like finite element base or finite element, finite volume, to approximate function by associated hypercube, if you will. So we are not talking about just space and time. We are talking about general parameter P, which is as big as 1. So give me the basic definition. X is the input, output is Y. Everybody understands Wx plus B. So that's a linear equation. The W is the slope, B is the intercept. So the conversion will be what's A? A is the equation. That is a beautiful part about neural network would be you can pick anything you want. You start with something linear, and I'm going to show you the linear relationship because it's easy to show. But you can make it non-linear, depends on how you pick the equation. It just start with linear relationship, but I can make it more linear by picking a particular activation function. And without going to algebra, this is what you learn in high school or college, right? And this is called ReLU activation function. ReLU activation function. That is your A operator is given a maximum between 0 and Wx based on this. Okay. So that is the relationship between linear and a machine learning or deep learning function. So you can have all kinds of functions that you can think about. If you really talk about, if you know your solution, you know how to pick the activation function. Okay. So how does it work? Okay, on this one. So you can think about what would be my blue box is my linear activation function. It has weights W1 and B1. If you output here is another neuron here using the red W2 and B2, and that is our output. So that's an operation. It's a recursive relations. That's the reason why you need to do hardware so that you can do it fast enough. Because you're not going to do it by sequential solutions, and that's where the hardware comes to the picture on it. And you can see here would be if I set B1 equal to B2. I basically have my M is W2 times W1. Just make life simple. Then you can understand, how this is going to work. But in fact, what you learn is nothing more is a linear regression. So we're doing regression. I'll just give you the idea about regression, how to put the mathematics together. And I put up a special issue on this one here. And I'm going to talk about these two papers, but before I go to great detail, what it is, and what is kernel approximation, how is it related interpolation theory. Okay, so this is what I'd like to say here, again, will be, I start with something called finite element, which is, I start with linear finite element, because I've been talking about linear in this case. And hidden finite element is create a deep learning neural network to reproduce a sample of integration functions. Now, instead of doing the weights and biases, I'm going to relate the weight and biases to the coordinate. That's how we run that problem. So the loss function is basically the residual, is a weak form of the system. And now, instead of just solving for the displacement, for example, the solution, I could optimize both the coordinates and the solutions. So that is the part we're looking for. And this is the paper right here. So you can think about would be, if you talk about a simple finite program, you equal your material properties, microstructure, whatever you want. If you go through your classical interpolation theory, the output is discrete stress and properties, and there's a solution, there's a solution. You basically will be, you have a set of coordinates right here, and the solution. But now you want to optimize your x and u at the same time. And that is a difference. But now we're going to replace this by but I don't want to replace it by a classical neural network, which, say for example, P physics informed neural network. That's what they do. The problem with that would be you don't have any mathematical proof that you can get unique solutions. Or sometimes when the system is getting too large because it's a black box, you cannot get any solutions. Okay, so explain what it means here would be, this is a partially connected neural network because I get rid of these two. And I'm going to write these weights and biases in terms of coordinates. Okay? And you can see here would be, So when we vary this coefficient, you can see my function changes. And then the same thing here. I'm going to vary this and vary this. This is supposed to be keep on changing. And similarly, when I do to here, you can see this changing. You understand how these weights and biases change as a function of x coordinate, because I relate the weights and biases in terms of x coordinates. So now I have a classical head function, but instead of writing in terms of weights and biases, they are in terms of the coordinates. So this is my linear finite element interpolation. So that's the way I relate them to the classical linear finite element. If you think about this, this is one hidden layer, the second hidden layer, input layer, output layer. Now, how I'm going to put them together as a finite program is element number one. You can do the same thing too. Now you have a finite program. But this can be done easily with Python. This is a little more mathematical, so you can put in a computer code program, and you can solve it the finite element way, or you can solve it using the full backpropagation gradient way to solve the problem. But I will not go through detail on this. But the whole idea here is you can solve it in numerical way, or you can solve it in a finite element way that you want to understand. Okay. Okay, so that is more or less what I said here. If you talk about one-dimensional finite element, it's element E. This is my element shape functions. But I don't have weights and bias anymore because they're in terms of coordinates. And you can think about this is my simple finite element program. So you can actually just use a standard theorem to get a solution. But if it's a simple system, I can solve it faster by attaching this into the finite element program. But if you have a much larger system, that this one iterative scale is a big one. So what I just give you say here would be we're going to write the weights and biases in terms of coordinates, and the loss function is basically the potential energy on a physical system. You solve for this. But when you solve for this, you solve not just a solution, you also solve for the input coordinate case. And you train it, that is the key point. Solve and train basically the same. And that is the engineering solve for fusion. And you have something called auto differentiation. If you want to make life more complex for your activation functions. So those will leverage the hardware that's done for us. So this is something that we actually input this into Abacus. So we basically change our element shape functions. And you can see will be, I use this reference solution Abacus about 10 million degrees of freedom. And you can see I only need about 20 getting within 2% of the accuracy. Because I optimize the coordinates. So that is, we're talking about here, if you compare this one and the accuracy within 2%, but this is a very small fish. Okay? So this is a little bit larger problem, and this takes a little bit more percentage, but again will be within 2%. But this is 10 million degrees of freedom versus about 46,000 degrees of freedom. Because we actually know where the location is, I don't need any adaptive criteria because it's trained. So this is more or less like measuring method. Okay, you can basically train your coordinates so you can get a compression ratio, just like measuring method. I'll give you and that will be a lot more than 25%. And again will be this one here is the overhead that you will get. These are all done by students, so you really need to find some computer science people to write this program to a lot more faster. So that's a key. So in my paper, that we actually reproduce Arcadia, Cubic Spline, NERD, IGA, it's all given there already. Generalized spline element, you can, because in universal approximation, once you understand, you can do it, but I need to introduce three operators, what we call the linear operator, multiplication operator, and inversion. Now you can build up any function you want, but it's a lot more complex. So there's a different way to really understand this. So that we go into the next metric. It's called convolution hidden. So this is my RAPM functions in 3 dimensions. That's a lot of. Okay. So there are many ways you can solve the problem, but in terms of mathematics, that is the way we come up with any interpolation function, and that given in this paper. And let me talk a little about this. So this one just published 2023, and this is just this year. I call convolution. So what I give you so far is a 2 hidden layer. In mathematics, you can actually show that if we satisfy certain conditions, this is all mathematical proof, 1 hidden layer is good enough. And usually that's called the Fourier, because any function can be represented by sine cosine function, Fourier expansion, assuming that you have certain understanding of the approximation of the solutions. So 1 hidden layer is good enough. You can show that if you have infinite number of neurons in 1 dimension, you can represent this as a Fourier layer. So you go to 2 layer, that's what I showed you here, will be a limited solution. If you go to 3 hidden layer, that's the maximum you need to do. That's a steep you need. But of course, you can do more, but you don't have that much interpolation what it means. So we start 2. I just showed you how you could break down the neural network into elements you can call or segments. But now I'm going to add in the 3rd one to come up with some hierarchical deep neural network. That's what I call hierarchical. But this is based on convolution theory. So this is what I've done for you in 1 dimension. Okay. When you go to multiple dimension, I introduce 3 operators. Linear operator, addition, subtraction, multiplication, and also the inversion operator. By that, you can build up any dimension you want. Like I said, n dimension, not just space, time, but it can be space, time, parameter. So this is what I have for the classical linear finite element. So that is what this one build up. That's your linear finite program. It's very simple. Then you can ask the student to do the homework on this one. That's a classical piecewise linear approximation. Now, can I do it better? Let's keep on. Okay. Let's go to here. So let's just look at 1 element. So like I said, you have many neurons here. I'm going to add in the 3rd hidden layer. That you need to do the operators, the multiplication and division operator come in the picture. And now, depends on how you define your neurons. I want this to be as long as I want, in any direction I want. That's the reason of the convolution. You can think about it as a 1-dimensional convolution of this hidden layer. And I call this connection is the convolution tangent functions. They are hierarchical functions. So this one here, for 1 element, depends on how I'm going to connect how many neurons I want. That's where the magic happens. So you understand my matters on this. So now you can think about this one is my new element, convolution hidden. I just say I connect to the 6th neuron. And then this segment also say W line is in 6. But this neuron will connect to this one. So that's where the connectivity comes from. So you can think about what would be in mainstream method. You move around, you cover different nodes in a different way. But the programming, you need to learn about graph theory, because that's a graph. So how you're going to connect it is like a graph. I'll give you one example here. So this is my segment or element. So look 1, 2, 3, 4, 5. My patch 1, I call it divided by S. So now this is my controlling parameter, just like neural network. Okay, you can have different activation function. I can change the activation function. Instead of connect everything together, I'm going to control the connectivity by S. We can think about this as a local, but this integer. So S02, I connect 1, 2, 3. And connect 2 elements. So that is the red line. In the green line, 2, now I connect this to the 4. But it can be arbitrary, so it depends on how I define S. So you can think about in mainstream method, RKPM is your dilation parameter. But I also have dilation parameter I cannot really talk about. The larger the S, the more connectivity, the more expensive it is. But that's the reason why you do by GPU. If you don't do by GPU, you won't gain anything from this case. So if I go into detail here, so this is just show you, look 1 cover 3, look 2 cover 4. So this is my one element. I call convolution in an element. We want to call this in 1 dimension. Or if you go to 1 dimension, you need to do matrix multiplication there. Okay. I will not go through all this thing here, but you get the idea on how it's going to work. And the paper is published already. There's some detail when not published there because we're fine. Okay. So this is a 1-dimensional productivity. You can do it in local coordinate, global coordinate, just like any finite element, but that's a new element. And I have a parameter called SAP. P is order polynomial. So that is a beautiful part here will be, now I introduce small parameter and our activity, H activity, depends on how you do all this. So basically it's a newer version of finite element, but from deep learning. So again, we solve, we train, and call this entering solve with human element. Okay, let me explain the difference between our method and this method. This is a classical finite element, linear finite element. It is a 9 by 9 by 9. The multiple algebra is 729 nodes. This is P equal to 4. You trust me, this is about close to 36,000 nodes. And that's what matrix looks like. Now, go to our element. For P equal to 1, S equal to 1, same. For P equal to 4, S equal to 4, same number of nodes. But I get back the same order of convergence. That is more complex, much smaller system. Because instead of solving 36,000 degrees of freedom, I solve 729 degrees of freedom. But of course, okay, my S is the connectivity, that means my bandwidth is much larger. So it depends on the solution scheme, iterate scheme, whatever you want. And I think that is a key difference between what we do and the classical finite element. And because of this, you can remove locking. Even I can start with saturation element, I remove locking for this problem. And if you really look at the solution time, these are degrees of freedom. Say S equal to 2, people can see the convergence rate, 2. If you do linear finite element this way, using S equal to 1, P equal to 1 is a lot more accurate than finite element. In terms of the number of degrees of freedom, I have 20 times less. For this one, I have 200 times less degrees of freedom to maintain the same error. Okay? And this is a computational time. Okay, and you can go about 5 times. And the key part is this is a trade-off. So that is a speed up. But like I said, at the beginning, you don't get any speed ups for small systems. But for larger system, you have a lot of speed up in this case. It's a dynamic problem. And we talk about the reference solution is about 1 million degrees of freedom. I can solve this problem with about 1,000 degrees of freedom. These are the references that is related to what I talk about on it. Okay, let me go to the next topic. Why tensor decomposition? What is tensor decomposition? What does tensor decomposition can help me? Okay. But you probably learn a lot about tensor product. Okay. Let me give you a brief review. What's tensor product and how is it different from tensor decomposition? If you look at a hardware problem, they borrow this idea of mathematics, but they're in hardware. Okay, so there are a lot of GPU computation based on mathematics, they build up the GPU based on that. Okay, let's just go back to linear function. Right? Linear interpolation is A0 plus A1x. Right? You need to solve, but now when we solve, it's a learning. In this case. Okay? So if you talk about bilinear element, it's a product. Right? So you have 4 coefficients. Because a complete polynomial, that's squared 2 to the 2. When you go to 3 dimension, you have 8 samples to the 3rd power. So if you go larger and larger, it's exponential growth. That is the good thing or bad thing about tensor product. Now, can I do this by separation variable? So for a 3D problem, XYZ, which is linear, X, My, and C for each directions. Okay, now I'm going to do a tensor decomposition. So now instead of 8 parameters, I have 6 parameters. Because you add them up, it's a linear growth. So what happens if this does not work? You get more modes. So the way I define modes is my neural network. So now you can come up, design your neural network to solve the problem. So now you can see here would be the parameter is number of modes times the addition of your dimension. Okay. So this is only space. So we're going to talk about space right now, and go to space time and then space time parameter. So this is a homework problem for students. They need to turn in a homework set about not grade. So if I have this system, fxyc is governed by 5x squared minus y cubed plus xc, and there's a range. So what is the function? Basically, it's interpolation theory, right? That's all it is. Okay. So you need to find the coefficients. If you do the cubic polynomial, you need 64 parameter. Right? If you do it by separation variable, you only need 12. Look at the solution. You go 1 mode up to 3 modes. Okay, your prediction error is almost pretty small. But the whole idea, this simple example showed that you save about 50% of the parameters in this case. But of course, it will be when you really try to compare the exact solution to this, they're not that bad. But you can take more mode, you can get it. In fact, you can use singular wave decomposition to prove that they're mathematically the same. So the whole idea here would be, I give you a concept called tensor decomposition. And this is basically would be, if I do a cubic representation, it's a third order replaced by 3 one-dimensional vectors. So the definition of tensor decomposition is given by a green line. You decompose a high-order tensor into the sum of product of one-dimensional vector. So that is some approximation that we do, but there are a lot of things we did not really investigate yet on how to approach this is the activation functions. So in terms of neural network, that's the way it's set up. The key thing would be now you can extend the tensor decomposition in such a mode you can actually come up with a neural network. Each neural network is designed the way you want it. That's the key point. Okay. So we're writing a paper on this one here, and we particularly talk about space-time parameter. Okay, let's just see here how we're going to look at this problem, because it doesn't have to be the same approximation or the same neural network. You can pick the one you want. So we are working on answers. We are writing special program that interface with answers. Once you get it done, you can use whatever answers has to solve the problem on it. Okay. So this is more or less called data-driven approach. Answers call this answers to SIM-AI. So SIM-AI has 4 steps. You use the classical finite element code to make many runs based on parameters. So now you need to think about combination of parameters. Like I said, if you do it this way, it's exponential growth. So you need a lot of large number of simulation. That's number 2. Number 3, you need to store them. That's this story. So when we try to compete in develop software 2.0, there are 4 things you need to think about. One is accuracy. Can I get back same accuracy or better? 2 is speed of solutions. 3 is RAM memory. 4 is disk storage. So those are 4 things that you need to compete. And most of the time, if you try to solve, you get all the data. Now you got data, big data. You train the neural network, and a lot of times you don't use it back. So it might not work. So what we like to do here is our convolutional AI. It's a complete new approach. We solve the problem altogether. No need to generate offline data, but the offline data basically is a solution. But before I do a solution, I need to calibrate my physics. Because there are certain things with equation might not work, so you need to calibrate physics. That's where the calibrate comes in the picture. Okay, now I'm going to solve in space-time parameter space. But we're using tensor decomposition. So instead of exponential growth, I only get linear growth in this case. Okay. So to give you an example here will be large-scale simulations. Talk about simple elasticity equation. to this. So this is the rapid era of energy. This is the degrees of freedom. For finite element with one single GPU, the next one we can solve with one single GPU. Okay? But I can solve up to this one. This one is 1 million by 1 million. I can solve it in less than 1 hour with one single GPU. This one is 10 million by 10 million by 10 million. And that is the comparison on the energy, norm, era, GPU seconds. This is the final element. Up to here, you cannot get any of this. This is impossible to solve. You can solve extreme complex geometry with extreme fine voxel mesh. I do not talk about here is this era and GPU in seconds. So what we have done actually is solving 1 million cube, 10 million cube. This one less than 1 hour. This one is less than 1 hour. But with one single GPU. So let me show you the convergence rate. This is a pretty classical way. We have the mathematical theory from interpolation theory, or next convergence theory that I can borrow because it's nothing more than that. You can see we can get convergence rate. But if you do it by finite difference or finite element, the number of real points is extremely expensive. Because now this is space-time. It's a 4-dimensional exponential growth in this case. So I'm going to solve this problem. This is not more a heat transfer problem, which is an eddy manufacturing problem. I have 3 space, x, y, z, give you the range, time, and 4 parameters. I'm going to vary this about 100 each. And my private solution in tensor integral form is about 5.6 hours. Once you get this, you get the solution. So when I do an evaluation, function evaluation, just like any finite element, it's about 50 milliseconds. But this is a very small problem. Very small problem. Okay. And you plot the movie, that's what it is here. And it depends on how you want to do it. That is something that we need to learn with computer scientists, how to do it faster. But inferential time is everybody. Now, put it together for this problem. The number of repeat analysis we don't need to be solved. This is if you use the classical finite element. There's another program we're going to talk about based on variation model scale. And all this you cannot compute. You don't have enough storage. And you can do this in very, very still up. So now you do a parametric space on a problem because I have 4 plots, I vary them. I get a function equation and space time problem. This is only a very simple problem. It's a big problem. But generate tremendous amount of data. Not only that would be if you do this finite difference gamma code, this is a formula code. These are step-by-step time integrations. I don't have step-by-step time integration. I solve it simultaneously. That's the key difference. So this is my summary. Okay. My summary basically say would be we are working towards what we call software 2.0, which is a unification of learning, calibration, and solutions. It's an alternative to the data transfer approach for product design and manufacturing. And right now, with a single GPU, we can solve 10 to the 21, which is city scale, which Jensen won't want to design the hardware to do it. But because our company reduced our model, I can solve it right now. And we want to do real-time and manufacturing problem. And real-time control from the problem.
Probably you want to ask something to this topic, and also his future opinion, anything. I think he can answer anything. You try to. Oh, okay, yeah. So anyone you want to ask a question, please raise your hand. Leo? The first one? Yeah, welcome to the microphone.
Very good topic, very good technique. I have a question. It's about you do this kind of very large computation, but I'm thinking about that. It's not that easy that we can always understand how to determine the final condition. We can understand how to have the initial condition, but how can we determine the final condition if we don't have it?
Like I said, this paper is proper just this year. Okay, but we really try to do here is to come up with a vision. What type of problems that we want to solve? And if you really look at the technology evolution, it takes a long time. Okay, so in my review article on finite element, okay, that's where I started, is 80 years. Okay. And at the beginning, when you work on finite elements, the elasticians basically say, forget about it. You're wasting your time. But people keep on working on it. Okay? And in the 60s, still not that many people work on it. There were 30 years already, from the 40s to the 60s, because there's no computer. But computers started in the 70s. And go to the 80s, that's the golden age of the finite element. So you can say about for every single field, it will take some time to evolve. Not only that, the most important thing is education. The problem that I can see is there's so many technology being advanced, but we don't educate our students good enough. It will take a long time for them to really understand what you're doing. Okay. You can think about would be machine learning, deep learning, AI, come about in the 60s, even earlier, the expert system in the 50s. It doesn't really get to evolve until now, right? I mean, the whole idea would be, you need to have a vision. That's what I'm trying to say would be, it's a vision. Okay, and education is very important. And the key point is applications. If the industry think that this is important, they will do it. You can think about would be, there's so much money dumped into AI. Every single startup is more than $1 billion. Okay, we are doing a very small part of engineering, good or bad. So it depends how you define it. You know, our market is very small. Okay, but if you talk about applications, if you can come up with real applications that people like to look at, for example, 3D printing. The physics is so complex. Okay. They do need this kind of speed, accuracy, and resolutions. You can think about would be, do a 3D printing, we are talking about micron scale deposition. So you need to resolve micron scale within centimeter scale. I don't even talk about meter scale. Okay. Because mostly is for very high performance material. In fact, would be if I want to print a 20 centimeter cube material, it takes days for the printer to print. The question would be, how good is the material? That is a real problem. Okay? And can I do it faster? So that's one of the whole idea would be, and we really starting, say for example, composites started in the 60s or even 50s, composites, like polymer matrix composite. They're now in using it, but that will be started about 60s. So at that time, when you do some analysis of composite, people laugh at you. You're going to say, by the time you understand one small part of composite, I have 50, hundreds of new processing way to do composites. So, good or bad? So you need to think about what would be, but eventually, you want to get high performance products, you need the computations. So you can think about what would be, 3D printing have been existing for a long time, but it's very expensive to do the experiment, and they need to understand it. So that is the reason why they put money into 3D printing to do predictions. Okay. So like I said, everything is evolution. We are talking about technology transfer. Good or bad, it takes about 30 years or more for any technology transfer. I only can tell you about what I know about finite element evolution. If you really think about how many new technology come up within in the past 80 years. You can count with your 5 fingers. But you can decide how you want to talk about that. Not only that would be, say for example, measuring method existed for about 30 years now, like close to 30 years. You have period dynamic, all kinds of stuff that you might know. Are they really in the commercial code? How many people use it? Because the engineer refused to learn. It's our fault because we don't teach them good enough.
Leo, do you have a follow-up question, or are you okay? Good, what should I say? Conversation, good, I should say, conversationist. You ask any question, you give lots of thoughts. So, I'm going to ask one question, and you can generate lots of thoughts. Okay? Like
I want the audience to think instead of just focus on one tiny aspect.
Okay, so do we have any great students they can think? May I challenge? 你可以用中文，我可以帮你翻译。As Chinese you wish. Any particular or any audience? Any question?
What are some potential real-world application of hidden technology can be used? I have no imagination. What it will influence the manufacturing industry?
Well, if you look at computer science, and computer science are one of the interesting field, they know how to sell their products. And we all rely on computers and computer science. Good or bad, the good thing would be they always create new products that people can use. The bad thing would be every year they need to come up with new ideas, and it's not that many new ideas on it, to do it. So in terms of engineering, good or bad, we need to build the products, reliable products. Okay. So what you're asking, the question is, how can we educate our students so that they are just as good as the computer scientists? Okay. We rely on computers. When the computer changes the language, we need to change our curriculum. You can think about what we start with War 5, Fortran, Fortran 70, Fortran 90, and keep on going, and then we have any other program coming up. They come with so many new products because the area is pretty new, because computer started only in the 60s and 70s. Whereas mechanics started, I don't know how many years ago. many, many years ago. So it's a time lag, but I think it will be in terms of applications. There are lots of applications, in particular in manufacturing. So what we learn in mechanics is given the product, do the analysis, make sure it's safe. There's not that many manufacturing science or manufacturing analysis. I think that's one big direction that you can think about. That people now need the software to design manufacturing processes. I'll only show you one is the additive manufacturing. Okay. But most of the commercial products are experimental determined. Okay. But you can think about with material costs, manpower is getting more expensive. They need to rely on simulations. I mean, my colleague, Hierarchical, is pretty well known in dynamic analysis, in particular car crash. When he gave a lecture, the way he said it would be, when he started doing car crash simulation in the early 70s, he said, if I really want to crash a car, the car is about $3,000, the cheapest one. But $3,000 US at that time is worth a lot of money. $3,000, but when you try to do 100, 200 elements, it costs you about $3,000 to do a simulation. Right? So you can think about it takes a long time. I would say 20, 30 years. He's consistent on it. Now all the car crash simulations are done by computers. You can think about what it takes time to do evolutions on it. And that's to give you one example. That's the reason why fundament is new technology that's recognized as a breakthrough. Now, what's the next breakthrough? I do not know. So you need to think about it, and the smart people should think about what it is. Don't just study the book. Think outside the book. That is, you need to come up with a technology. I think that is what we need people to do is come up with technology.
This is a student, a real student.
But this will be good student that they can come up with new technology.
Then I don't know.
Don't say you don't know. You never know.
I should trust them.
我用中文问好，就是我特别好奇的是，数据是怎么得到的？就是训练的数据。因为我自己假设，我假设你的输入是有限元数法集，那你如何确认不同形状或者是不同材料的结果？因为这样子，你的数据就要透过跑很多很多次有限元数法，然后来得到。然后，对。就是这是怎么做到？您怎么做到混合不同材料或是不同的形状
？Okay. All right. Let me answer his question first, and then I'll enhance on his question. Okay. 它的数据啊，这个数据就是这个最重要这边 calibrator, trainer 跟 solver 都有 one shot 啊一起做掉啊。这数据是从哪里来？从计算来，没有错。但这个计算是可靠的计算。你刚刚问的问题就是他想解的，他那个 input p space 基本上可以有材料的口点，因为有 neural network 嘛，你要几个都可以，你要多少 range 都没有问题，所以一次就可以全部做完，所以就不用做那么多参数研究在有些人。But I will enhance your question a little bit. So the students ask about the data. How we come up with this training data, okay? And for example, I know from many industries they don't too many data, but data is always scarce, it's always limited. And how can you get a quality data so they can calibrate your work, so your simulation become reliable for example, particularly important application. What is all this tech and how many data do you need?
Data is expensive. Depends on what problem you're going to solve. So for the problem that I'm talking about today is data generated by, say, a PDE solver or 5 elements of PDE, partial differential equation. Partial differential equation is only an approximation of your engineering system or your scientific problem. Say, manufacturing. It's not well established. You can think about any manufacturing product. There's no manufacturing processing software. They might have some, but they are not complete. Even if you have the software to do it, it takes you forever to solve a problem. And the equation might not really give you all the physics. Right? So that is more or less you're asking for. How can I generate data that's reliable, that's useful? So in this figure here, I talk about 3 types of problems. Okay? The first type of problem is if you want to design a new manufacturing process, and then you need to come up with some scientific equation or empirical equation that represents the system. I call this type 1 problem. That means if I want this invention, new invention, I need to do some simple experiment with hypothesis. So the experiment would validate or invalidate your hypothesis. So that's a very basic steps. Okay? So if we learn in engineering, what people call would be, can I simplify my hypothesis by coming up with some dimensionless parameter, say Reynolds number, for example. So you need to come up with some dimensionless equations or dimensionless number. Okay. In fact, that's where the computer science people are trying to do. There are a lot of data science analysis, but based on data, come up with the governing equations. Okay, so that's the first step. Okay. Now to do that, you need to do calibration. I mean, assuming your hypothesis is good, you can come up with a represented, simplified, partial differential equation or just simple equations. Okay. But that equation doesn't really give you useful information for general design problem. Because they only give you, say, this is a function of second derivatives in time, mixed derivative x and y, whatever. But the data only tell you about that set of data, but would not extend it outside the range of data. Okay. So there are a lot of research work have been done. Actually, we published our paper in Nature. One that would be, given the data, how are you going to combine dimension analysis and some PDE solver so that you can come with the PDE, but in front of the coefficient of PDE, they come with some dimensionless number. Okay, we call it dimensional edge, dimensional analysis, but this is a way above. There's a lot more beyond that we can do right now. Okay, so that is mostly for some data that you don't know any physics. That I call this class 1 problem. Okay, class 2 problem is this one. Okay, you started understanding your data, but I want to extend the domain of interest so you can solve some bigger problem. Then you have some data, you have some equations. Because that is something you come up with. I call it class 2 problem. But eventually, you want to go from data heavy to come up with solving PDE. That's the whole idea. But we are not there yet for a lot of manufacturing problems on this case. Okay. So, but now you are in something that you need to come up with the existing PDE that's governed by Newton's law, for example. there are a lot of unknown coefficients. So you need to do some calibration. Once you validate your hypothesis, basically your Kaplan equation, with some uncertainty of your coefficients, you generate data. Right? And then you basically train the data. That's what most people do. But our approach is space-time parameter. So now we embed the parameter into your differential equation, so I can solve it together. So that is one approach that might not be the best approach, but I'll let you cover better if you can.
Thank you for this.